Okay, so I'm going to give you a short overview over my poster. So I'm not a SPIN student, I'm a PhD student in the so-called SIGA project, which is a project concerned about the effects of induced seismicity due to geothermal energy production. But during my project, I was applying rotational motion measurements, which I want to show you in the following. So the overall goal was to estimate the subsurface structure of the shallow subsurface, the velocity structure of the shallow subsurface, so about the upper 100 meter, because this is most important for side effects. So, for example, soft sediments can amplify the ground motion and therefore cause more damage. And my study area was Munich, because there a new geothermal power plant was built, which could cause induced seismicity in the future. And therefore, it's really important to get more information about the subsurface structure to see if there are indeed amplification effects like this. So generally, if you want to get more information about the velocity structure, you apply array measurements. And from the data, you can then extract dispersion curves from surface waves. The problem, however, is that such array measurements can be quite challenging because you need a lot of space in deploying them. And especially when you're working inside of a city, you often don't have the space to deploy large arrays. And that's why we wanted to test a new approach of single station 6-component measurements, which combined 3 translational and 3 rotational motions. And such single station measurements are, of course, a lot easier to perform. So we need a seismometer and a rotational sensor. And in our case, we're using the IX-Blue Size 3A rotational sensor. And then over the relation of translational motion and rotational motion, we can estimate the phase velocity of Love and Rayleigh waves. So since surface waves are dispersive, we can compute this phase velocity in small frequency bands and then construct complete dispersion curves. So in order to verify this new method, we simultaneously measured with an array, and here in this map you can see the locations where we performed those measurements. So it was always the 6-component measurement at the same time as the array measurement. And we were measuring ambient noise in a frequency range of about 1 to 20 hertz, which corresponds to urban noise, so cars, trains, construction, and so on. So in the following, I'm going to show you the results for this station up here. So like I said, from the array data as well as from the 6-component data, you can compute dispersion curves. So that allows us to directly compare the results. We analyzed the array data using high-resolution frequency wave number analysis and spatial autocorrelation, which are the blue and the yellow curves. And we also computed the wave number limits for the array to see the resolution of the array. And the Cayman half limit lies here, which is at about 3 hertz. So the data below this, you should not interpret anymore. Then the green curve shows the dispersion curve from the 6-component data. And you see that all the 3 curves overlap in a certain frequency range. However, at lower frequencies, we see quite large differences. So in general, we assume normal dispersion, which means that the phase velocity should increase with decreasing frequency. But we see that here the array curves drop, and that's just because it's outside of the resolution limit. But we also see that the 6-component curves drop at a certain frequency here. And that should not be the case. So the question is, why is this happening? And we can answer that by looking at the power spectral densities of the data. So in blue, it's the computed PSD for the seismometer data, and in yellow, the PSD for the rotational data. And what happens is that at a specific frequency, the self-noise level of the rotational sensor is reached. That means at low frequencies, the rotational motions are too small to be recorded by the rotational sensor. And that's exactly the point where our curve drops here. So we can only use the data in this frequency range here. In the next step then, we take the dispersion curves from the different methods separately and invert them to get the P and S wave velocity profiles. In this case, I constrained the inversion to a 3-layer model, and we derived the upper 100 meters. And we see that from all 3 dispersion curves from the different methods, we basically obtain very similar velocity profiles, which is really good. So we see 2 velocity steps, one at about 4 meters and one at about 20 meters. And when we compare this to a lithologic profile, we see that the upper step matches quite well with the groundwater table, and the lower velocity step matches with the boundary between sand and clay. So we see a positive correlation between the velocity and the lithology, which supports our inversion results. So we can conclude that our 6 component measurements give comparable results to the array measurements, which is a very important finding because single station measurements are a lot easier to perform because they require less space and time in deployment. So I hope I was able to convince you that rotational motions are very useful, and if not, I'm happy to discuss this further at my poster. Thank you.
Thank you.